So one of the most important areas that we are going to encounter as we progress through learning how to code for embedded systems is memory management, right? So in particular, one of the things that we need to understand over here is what are the different types of memory that are even available in an embedded system, and what are possible techniques that we can use in order to manage the memory. So first is let's recap this picture that we already saw of what a processing system looks like. You have this core processing system which has in turn an arithmetic and logic unit, a certain set of registers for temporary storage, and some control unit that tells it what to do, right? And usually what happens is this control unit in turn is getting instructions from somewhere, and that's where the rest of the outside world comes into play, right? Over there what we find is we have something called the main memory of the system, where the instructions come from, as also the data that is actually used for storing all the intermediate computations. There is also something called the secondary memory, which is usually more a long-term storage device, right? Something which has a larger capacity but is possibly slower than the main memory, right? So we use it in order to store things that we call files or other kinds of data, right? But the main memory is the working memory of the system, the one where I can actually create variables, modify them, update them, and so on. You will also notice that there are input devices and output devices that look very similar, at least in terms of where they are connected to main memory, and that is intentional. As we will see later, it turns out that the same techniques that we use in order to communicate with main memory are also useful for communicating with devices, that is the input and output devices. Okay. So ultimately what we have is we have computation, which is the ALU plus the decoding logic, and we also have IO, which is a bunch of peripherals and interaction with the outside world, and then of course we have our memory, right? So the memory clearly plays a very important role in the functioning of any computational system, not just an embedded system, any computing system, right? So among other things, any temporary data, variables and so on are stored in memory. The instruction code, the actual code that's running on the system, also needs to be stored in the memory. This includes things like an operating system if there is one, right? And on top of that, especially in the context of embedded systems, it turns out that configuration data, which is often a much simplified version of what is required for actually booting an OS, is also stored in some kinds of memory, right? It might be something as simple as some identifier which tells this particular camera or this Wi-Fi chip what address it is supposed to announce to the outside world. Okay. So there are many different types of memory that we need to be aware of as we get into discussing different kinds of embedded systems. So we are going to look at a few of those now, right? And the first term that you are likely to come across is something called RAM. RAM stands for random access memory, and what that means is that it is possible to access any location in that memory at random, right, without necessarily going through it from the beginning, and read it or write to it possibly in approximately constant time. Okay. So take a moment to understand exactly what that means. All that we are really talking about is I have a bag of words that are storing data, and I should be able to sort of address any one of them and pick an element out of it in more or less constant amount of time. Okay. Typically RAM is also what is called volatile, meaning that when we switch off the system, we lose the contents of RAM. Now the interesting thing is RAM is one of these it's a term that has lost all its original meaning and has taken on meanings that were not intended at the beginning, right? For example, whether it's volatile or not has nothing to do with whether it is random access, right? So whereas nowadays we pretty much think RAM, it is volatile. You switch off and the system loses the data in RAM, right? That's typically the way that we think about it. But the important point is we also think of RAM as sort of being the opposite of ROM, which is read-only memory, which is completely incorrect, right? There's no connection really between the two. RAM could be read-only, right? And a ROM could be something which is not random access. The important point is that the usual contrast of RAM is what is called serial access or SAM, which is not a term that you are likely to come across often. An example of that, the most common example was what is called a tape drive, which it's very unlikely that any of you have actually seen a tape drive for computer storage, at least in action. Some of you may have come across a cassette tape which can actually be used for playing music. If so, you would know that in order to reach a particular song, the only way is keep sort of pressing the forward button until you reach the beginning of the song and hopefully stop at the right time, right? You cannot just jump to the beginning of the song and start playing it as and when you would like. To some extent, a book is similar. Although a book does have random access capabilities, I can jump to any page in the book at any point. But if I want to, for example, read through the book, I usually need some kind of indirection. I need to probably read through it page by page, right? So a book is in some sense closer to RAM than to serial access, but tapes are very definitely serial access, and those were the real contrast to RAM. Nowadays, as I said, RAM pretty much just means the working memory of the system, right? You use it to store the program runtime. Everything on the stack, the heap, the temporary variables, dynamically allocated variables, arrays, all of that goes into RAM. Anything that basically does not fit in registers. Okay. So for any computing system and also for embedded microcontroller based systems, the RAM is going to be a very important point of your design, right? You need to know how much RAM is available in the system, because that tells you how much data you can actually store as your variables while you are actually performing computations. Now ROM, read only memory, and another variant of ROM called EEPROM, the electrically erasable programmable read only memory, are things which are technically a variant of RAM, but you don't really call them RAM. The important point is they are non-volatile, and what that means is even when the system is switched off and you remove power from it, they retain their value, right? And they are essentially not programmable, meaning that they are sort of created with a certain content and that's it, you cannot change them after that, right? EEPROMs are slightly programmable or programmable to a limited extent. You can update them at an infrequent intervals, but it's primarily used for sort of storing things like configuration information. You might have come across this concept of a MAC address, or the media access control address, in a network device, Ethernet card or a Wi-Fi or Bluetooth, right? And this MAC address is usually something which is supposed to be unique to every network card. And very often what is done is that's usually put in some kind of a ROM kind of device. Nowadays it is made slightly programmable, so you can sort of get around that one-time creation, but at least conceptually it's supposed to be read-only. You do not modify it once it has been created. So EEPROMs especially are found typically more often in slightly older kinds of microcontrollers. Nowadays, to a large extent, what we find is this something else called flash, right? Flash is probably the most common kind of non-volatile memory that is available in microcontrollers and is used for storing fairly large amounts of data, right? It has high density, it can be used for large amounts of data, and it is non-volatile. What's the catch? Why can't I just use it instead of RAM? Well, it's not as fast as RAM, right? I can use it to store data, but it does take a significant amount of time to write data into flash memory, and maybe not as much to read data back out, but definitely more than the time required to read or write from the regular memory that is used as RAM. Flash turns out to be highly programmable. You can typically use it thousands or possibly even millions of write cycles, and in most cases it has largely replaced the use of PROMs or programmable ROMs, except in specific use cases that still exist. Right? So lots of things can be stored in the flash, the program code, configuration and so on, but it cannot be, or rather is typically not used for things that are changing at runtime. So if I create a new array or a variable, I am almost never going to directly write that into flash, right? I will probably only after I have sort of finalized what the value is, I might store it as a file into flash rather than just trying to write it as an addressable area in memory. Now there are other types of memory that you might come across in different kinds of microcontrollers. there are things called FRAM, ferroelectric RAM. Especially there are a series of microcontrollers from Texas Instruments in the MSP 430 series also. They provide a nice form of unified memory that can store both the program code as well as non-volatile data. What I mean by non-volatile data, for example, is logging applications. Let's say you are just collecting data from a sensor and you want to store it for a large period of time. FERAM actually allows you to store fairly large amounts of data like that and in a non-volatile manner. Right? There are other newer technologies like phase change memory and MRAM, magnetoresistive RAM. Right? The problem is those are typically, at least at present, these are much more expensive than the flash and RAM combinations that we usually find in other microcontrollers. And microcontrollers tend to be a very cost conscious market, so it's very difficult to really make significant changes easily in them. So although you might find occasionally a microcontroller with different kinds of memory, the most common ones that you need to be aware of are how much is the RAM in the system, how much is the non-volatile storage, which is usually flash. So with how data is stored out of the way, let's look at the actual problem of memory management by itself. So the first question, what do we mean by memory management? You have a lot of data that gets created during the running of the system, right? There might be temporary values, arrays, sensor data that is getting picked up by sampling a sensor or an A to D converter. Either you want to actually process it, or perhaps you just want to buffer it and transmit it to some other host. And the problem over here is the data is too big to fit within the registers of your CPU, but at the same time you also want to be able to store it in a place where it can rapidly be updated, either processed or ready for transmission. So I don't want to put it into non-volatile slow storage. I want to keep it somewhere where it's readily accessible and I can just use it whenever I need to. So why do we need to do this memory management? Ultimately it comes down to we have a limited amount of storage available in any embedded system and we would like to make the best possible use of that, right? And here we have something to consider, which is that the decision on how to store the data, where to store the data, what data to store can be done in two ways. Either you do it at runtime as and when the program is running, or you do it at compile time ahead of actually deploying the system, right? And what are the sort of benefits and drawbacks of these approaches? The first that we are going to consider is what's called static memory allocation. This is before the program runs, the allocation of memory, where data is stored, how it is stored, how much space is allocated for storing the data, all of that is decided not by the compiler but by the programmer and implemented by the compiler at compilation time. In other words, in the context of C, basically what we are saying is we do not have malloc, right? You cannot just ask for a block of memory while running the system. You need to have allocated all of it as static arrays ahead of time before you actually deploy the system. What that means is that this kind of static allocation is going to remain in memory for the lifetime of execution of your system, right? Because you have to create your arrays as soon as the program starts, and you are not allowed to create any new arrays or variables because there is no means for creating new variables, except perhaps for function calls, which could be very small amounts of stack memory that you have. So the advantage of static allocation is predictability. All the memory that you need is just allocated at compile time and does not change at runtime, right? This in turn leads to something where we don't have fragmentation. Now, what is fragmentation? We'll get to that in a moment. So just hold off for understanding what fragmentation is until we look at that example, right? But not having fragmentation, and presumably fragmentation is a bad thing, otherwise I wouldn't be talking about it this way. We'll see why it is bad in a moment, but the good thing about static allocation is it avoids the problem of fragmentation, okay? It also means that you have lower overhead. For example, I don't really need to check whether a particular index is inside or outside an array at runtime. I can do it at compilation time because I know the sizes of all my arrays at compilation time, right? And I know exactly whether a particular index is going to land inside or outside a particular array. Well, there can be dynamically computed indexes that you still need to do something about, but it solves many of the problems that you could potentially have over here. Now, all of this, when we put it together, what it means is that in the context of embedded systems, it gives you simplicity, which is a very valuable benefit in the context of how you implement a system. You have fixed memory layout, and addressing and access of memory is performed through very simple computations. It's also reliable, and why it is reliable is there is no possibility of a memory allocation failure. If the system has started, it means it has already allocated all the memory that you need, right? So at least if it's failing, it's going to fail reliably. If it couldn't allocate enough memory, the system will never start. So you at least have a known failure mode. Especially in the context of things like medical and automotive, where you have safety critical applications, this becomes important because it means that you are never going to end up in a scenario where at runtime you try to do something and it fails because you ran out of memory. Okay? It also helps with real-time applications. There is no runtime overhead for allocating memory, right? Defragmentation or fragmentation, something that we'll be talking about again. There is another concept called garbage collection, which also comes into play when you are talking about memory allocators, right, or how you ask for memory at runtime, which we will not really get into any details of over here, but can play an important role in actually slowing systems down if you're not careful. Java, for example, uses a concept of garbage collection in order to free up memory that is no longer being used. So does Python. So those languages automatically have potential problems in terms of the fact that the garbage collector may kick in and start to slow things down when you don't quite expect it. There are ways of getting around it, but you have to get around it. You have to basically plan for that. What are the possible drawbacks of static memory allocation? It's relatively inflexible. Everything that you want to allocate must be known at compilation time. And you could also end up wasting space, right? You allocate an excess of data that is not really being used. Scalability, especially things like dynamic data structures like trees and so on, can be used in order to handle certain kinds of data growth very efficiently, but you can't implement at least they're not easy to implement using static allocation. And it also potentially means that there is excess development complexity. If you want to change the amount of data that your system can deal with, you might have to go around changing it in multiple places. You can't just change the size of an array and be done with it. That could have multiple impacts in various parts of your code. Alright, so static allocation looks, so far we were looking at the benefits, but finally we did see some drawbacks. What's the alternative? Dynamic memory allocation. And as you have probably seen from the actual C programming course, right, malloc and free, dynamic memory allocation plays a very important role in actually having arrays and data structures defined at runtime. So you allocate memory at runtime, and in the context of an embedded system, let's say you are trying to do data logging, collect data from a sensor, store it into a buffer, and then finally send it out over a network, or just take data from one side of a network interface, buffer it, and then send it out on another side, right? All of those are dynamic data. You don't know how much data is there until it actually gets to you. How it's implemented? Using a bunch of keywords in or functions that are there in C, right, usually provided by the standard library. They provide pointers to you that are allocated at runtime and are not known at compilation time, right? And this basically gives you some freedom. It also gives you possible problems that you need to deal with. One of the important things is it requires a runtime allocator. So there is some other function or some other code that's actually running each time you call malloc, which decides, okay, where do I find the right chunk of memory that I can give to you as a pointer, right? It's not just malloc, every time you call it, it just gives you a number and hopes that there is memory there. It has to make sure there is actually free memory at that point. So that's an allocator, and how you use it starts to matter in terms of runtime behavior as well. What are the advantages of dynamic allocation? Very simple, you can adapt to the actual usage scenario, right? With a single code base, I can actually target different microcontrollers which have different amounts of RAM I don't need to say that, hey, I'm designing for something which has only 1 megabyte of RAM. Let's say that later I change to a system which has 4 megabytes of RAM, everything just works. I don't even need to recompile. Okay. It also can help when you are trying to deal with something called average case versus worst case scenario, because very often you might find that, especially with buffers and so on, the average size of the buffer is actually pretty small, because most packets that come into your system get processed very quickly and sent out. It's very rarely that you start accumulating data, right? Maybe the network processor downstream is not ready to receive data from you. What do? You could drop a packet, right? It's not critical. You might be able to get away with something like this, in which case you might actually be able to get away with designing for the average case rather than the worst case. Okay? So there are a number of advantages to dynamic allocation. One of the biggest problems though is what's called fragmentation. So what does fragmentation actually mean? Let's look at an example to understand it, right? Now this picture is basically showing you the total available memory to a processor, right? I'm just drawing it like a big rectangle. What it means is there are some addresses out here. It would start from some address 0 up to, let's say, some FFFF, some large number out here, right? So all of these are assumed to be addresses. Convention once again to think of this as low addresses, high addresses, right? There is big endian, little endian. We don't care about all that right now. All that I care about is every single location over here has an address. And if I wanted to get data from there, I would need to have a pointer that points to a location, and then I can access it and pull data out. And when I call a function like malloc, what it's going to do is basically take a chunk of this memory, reserve it for me, and say here's a pointer to the start of this memory. Okay. So that's basically what malloc does. Let's say I call the malloc function. It takes a chunk of memory that's available somewhere in the system and says, okay, go ahead, use this memory. Now I call malloc again 2, 3, 4 times, right? And each time it basically gives me the right sized chunk of memory for whatever I requested. It's possible that not all the sizes are the same. So malloc 1 was pretty big, 2 was not so big, 3 was actually pretty small by comparison, 4 again was pretty big, okay. All these depend on the sizes of some variables that I am trying to request. Okay, so now I have done 4 malloc calls. I have allocated most of the memory in my system. Now let's say that I am done with some of my work and I free the unit 3. Effectively what it means is this memory is now free. I don't need this chunk of data. I can do something else with it, okay. But now what happens is, let's say I get a request once again for malloc 5. When I freed malloc 3, I did not move malloc 4 up. I just left malloc 4 where it was because it's already being used. Moving it around would require quite a lot of work, okay. So it's usually not done by default. But then what that means is when I request malloc 5, it fails, right? Because I don't have space to fit it here and I don't have space to fit it here. But if I had managed to move malloc 4 up, that is that chunk of memory, if I had managed to move it up, I do have enough space for 5, okay. This step over here, this is essentially called fragmentation, right? I've got my overall memory broken into parts where the total remaining memory is big enough for what I want, but there is no contiguous or consecutive set of address locations that is big enough for what I need. Okay. This is a very real problem. Every single computing system does face it at some level, and usually in operating systems there is some part of the kernel that is handling this kind of fragmentation. It actually takes care of free blocks and tries to rearrange them, move data around and so on in order to prevent this problem from happening, right. So fragmentation can be a very serious problem, and it happens because of dynamic memory. All this happened only because I was trying to allocate memory at runtime. So what happens as a result is I basically have unpredictable memory usage. I can, for example, let's say that there was a loss in the network connection at one point. Suddenly your packets start buffering on your device, right? And you need to decide, am I going to throw it away or not, okay? You could also have a scenario where there are memory leaks, right? If I malloc and I don't free the data after some time, it's even worse than defragment or fragmentation, because it means that I'm just holding on to memory that I'm not using, and somebody else who actually needs memory will not get memory when they request it. Yeah. So if you do not do proper dynamic memory management, you can actually end up with runtime failures, right? Failure to allocate memory can cause a system crash, right? And this can have very serious impacts on the overall behavior of the system. And you also run into this problem of non-determinism, which is that you could have a scenario where, because you need to defragment the memory or you need to do some garbage collection or some other kind of memory management at runtime, a particular operation that you thought should finish within, let's say, a few microseconds might end up taking hundreds of microseconds because the operating system or the runtime had to do something else before actually answering the function that you called. Okay. So this can lead to non-determinism, which can have an impact on real-time performance guarantees. So the overall recommendation in general is to always use static allocation for embedded systems wherever possible, minimize the use of dynamic variables and structures. You could, and many systems do use this, have a scenario where you break up your memory into two parts. One is the critical parts, such as the operating system, the real-time constraints and so on, and the non-critical parts, which can be thought of as maybe network buffers, possibly data logging, signal processing, where in the worst case, even if you do not have data for that, you just sort of drop it and say, okay, I lost some information, but my system hasn't crashed, right? So what are the different ways by which we can actually optimize the use of data, right? So far we have looked at memory management through static or dynamic allocation, but we also want to look at optimizations. One of them, for example, would be use the arrays of the right size and accumulator as needed, right? An example of that is, let's say that I have these values over here as all 8-bit values. I could have just declared them as an int array as well, and it would have functioned, it would have done the right thing, but it would have used up much more space in memory than I actually need, right? A similar kind of thing holds for, let's say you have for loops over here. You can see that, for example, this loop over here uses an int 32t, right? Now, was that really required? Is it possible that the milliseconds value could go up to 4 into 10 power 9, which is the range of values for a uint 32t? Possible, right? We can't really know ahead of time, but if you do know that maybe it can never be that big, you could have chosen a better data type which does not need that kind of size. Similarly, when I know, for example, that j can only go up to 1000 over here, do I really need it to be an int? Could I have used a uint 16 instead, right? Possibly. Here it's not so obvious which is the right one to use, because like I said, it might also depend on what kind of registers are there in your system, and unnecessarily imposing the wrong data type might actually end up hurting rather than helping. So other optimizations that you could use, right? Global variables, like I said, tend to go on the heap. They are in some sense competing with any malloc kind of operations, right? They are there for the lifetime of the program. There is no deallocation. Global variables always exist. So where possible, always use local variables. You allocate them on the stack, and once the function is done, it exits without having any further impact. Static variables are sort of, compromise between global and local. They are similar to global in the sense that they also occupy space on the heap. They occupy space which is also used by malloc kind of operations, and once you have called a function, they pretty much remain over there, right? So it's not as though you are actually getting away from the problems of global variables. The one other issue that they do solve is that a static variable is only accessible inside the function that declares it, right? So at least in terms of compartmentalizing and making your code modular, they do help, but from the point of view of the actual usage of memory, statics and globals are very similar. So one other thing that is often done in the context of programming is to use data packing, right? Especially in embedded systems. An example of that is, let's say that you have RGB, red, green, blue data, which is being used for the bits corresponding to, let's say, a color, a VGA display or something like that, right? 16-bit RGB data actually has a way, or you can actually have 8-bit RGB data, or in this case, yeah, I think it's 16-bit RGB data that we are talking about over here, right? I have three numbers R, G and B, and even though I have declared each of them to be 8-bit values, they actually need to get compacted into a single 16-bit value. And what I can do is I can actually declare a uint 16t to hold the packed data, and by using some kind of manipulation of the bits, shifting them right, left and so on, I can get the correct set of bits that are required for red, green and blue and pack them into the correct locations, right, in a 16-bit value. Now obviously 8 plus 8 plus 8 is 24, whereas what I am getting out here in packed is only 16. There is some loss of information, but that's part of the deal, right? 16-bit RGB does have the capability only of representing 16 bits worth of color, right? This helps because it sort of makes more efficient use of the memory that is available to you. Rather than using 24 bits, we actually use 16 bits, and it turns out that that's good enough for a lot of the color perception that is required for us. So optimizations like this can be useful. And as you can see over here, right, it all involves taking data and shifting it around, moving it from, moving the bits around so that they can be packed appropriately. This is also something very common that we will see multiple times in the context of embedded systems. Another optimization that you could use is some form of pooling of data, right, where essentially what we have is that you, like I said, you could have some static arrays that are declared up front in order to use the for use by the operating system and libraries, and another chunk of memory that is basically set apart as dynamic space, and this is available as a pool that you can use for allocating buffers and so on. Possibly, even if there is a failure in your dynamic space, it is unlikely, or rather it is not possible that it will affect your static allocation, and therefore your operating system itself continues to run without problems. So to summarize, memory is one of the most important and limited resources in embedded systems. There are different kinds of memory. The volatile, non-volatile is probably the most important distinction that we need to keep in mind while deciding what to do with memory. There are many different strategies and best practices for efficient use of the memory, and understanding the difference between static and dynamic memory allocation is one of the key things that are required for actually implementing embedded systems.